Good morning. Welcome to Krishna's classroom. Let us continue from where we left last time. Recall that the last result that we proved was this. I just recall this result. If Fn is an extended real value non-negative measurable function, for each n, etc. And remember, this could be at some x equal to infinity also. Plus infinity. However, f is measurable. That you okay. Then integral over x f dmu. So this is what we proved last time. We will just take some applications. This is in the context of double series of non-negative numbers. It says irrespective of the order in which you sum, you always get the same sum. That means this is what we are expecting. Sigma I for Aij non-negative, one to infinity, j running from 1 to infinity, that means you are summing it row wise or column wise. Always get the same sum. It is first row wise and then column wise, and first column wise and row wise. I mean, I'll just demonstrate this. Now, this is something you can easily. Okay. So what we have already looked at the proof of this. So what we do now is look at the following. Take x to be just 3 elements. Okay. And the power separations. And mu we define mu of one mu of 1 mu of that means what we are doing is we are just giving the counting measure. So that means when you take the union of or take any subset of that, the measure of the subset will be equal to the number of elements in that set. So this is what is called the counting measure. This is called the counting measure. Now what one does is, you look at take Fi to be equal to defined by Fi of j equal to so three functions are there and each Fi takes a value, so it's essentially this one 3 1 3. You have got these lattice points. So you define F1 to be A11, A12, this is A21, A22, A23, A31, A32, A33. What you assert is that suppose you sum up these and call the sum as B1, B2, B3. Add them. If you add these and call this is as A1, A2, A3. Then A1 plus A2 plus A3 which means you sum this up row wise and then add them up, or sum this up column wise and then add them up, you will get the same sum. Okay. So we are defining functions Fij of this. Now what you can prove is this with all these counting measure etc. You see that let us just compute this. Say Fi this is what is Fi? Fi is equal to integral over x a I1 plus AI2 AI3 this is it. Now you know that this is a simple function and the integral counting measure, this is going to be A11 AI1, the measure of this mu of right. So that's how you evaluate. So this sum can be now written in the form of a, I mean that's important. This sum can be written as an integral, which introducing an appropriate measure on the domain of these functions. Okay, this is what's called the counting measure. So by introducing counting measure, you can define the sum as this. Okay, so and the point is this. Now I will come to the what we want to assert. So we'll just write down the theorem, general result that we want to prove. So corollary to what we have proved is this. If aij's are non-negative for I and j equal to I running from 1 to 80 and j running from 1 to 80, then j equal to 1 to 3, I equal to 1 to infinity. This is equal to sigma j equal to 1 to infinity, sigma I equal to 1 to infinity. Now, that means the two summation operations in this case from you, and it's important to observe that aij's are taken non-negative. A second thing that we have to look at is this: when aij's are greater than or equal to 0, that sum of this for some values of I, this sum may be plus infinity also, it does not matter. Okay, right? So how do we prove this? So we have to recast the whole thing into the language in which this problem has been framed. Let us see how we do this. Now I am sure it must be coming to your mind what to do. So we have to choose the appropriate set, the sigma algebra on it, and the measure. So it's the following: x is taken as n set of natural numbers, and on that p you take as a set of all subsets of which is a sigma algebra, and mu is taken as the counting measure. That is mu e equal to number of elements, the cardinality. May be finite or infinite depending on what E is. In fact, for singletons, it is going to be 1. So, mu of for each n, this is the case. Right. Now what one does is we transform this to the language of our theorem. So what we have to do, we define functions fi at j where aij is this for all I and j. Now you can easily see that fi's are measurable, extended, real value, extended real valued functions on x which are non-negative. In fact, non-negative functions on x. Okay. Now what one does is the following. Define gk of sigma j equal to 1, sorry, I equal to 1 to k fi k. Now this you define for k equal to 1. Well defined. These are again extended real valued functions which are non-negative, measurable, and therefore gk are measurable, non-negative, extended real valued functions. Now this is actually equal to, so you see that gk at gj is turns out to be fij is aij, so it is going to be I running from 1 to k that's what it turns out. Okay. Now what about what more information is required to apply the above theorem? It's not. It's now you immediately see that gk is a monotonically increasing function. It's a collection of monotonically increasing functions. Increasing non-negative functions measurable, So what happens? Limit G is exists as a measurable extended real value extended non-negative functions. So what do you have? You have integral of what is this? Is equal to limit this is equal to this is the theorem. And this of course is the following. So this is equal to this. That means the integration operation and the sum and the limiting process commute. Now if you rewrite this in terms of AIJs, then this is the two summation operations commute. Now I leave that little part to you. Okay? Convince yourself that this happens. So that's a so the important point here is this. Now we have introduced integration theory, and the integration theory actually takes care of the infinite sums also. Okay, there's a way of dealing with the infinite sums. As it can be written as the summation is essentially a disguised form of integration with appropriate choice of a measure. That is what this demonstrates. Okay, so there's a universal. So it's almost unifying integration and summation. Okay, right. So that's the remark. So integration and summation are uniform. That is the comment I have to make on this. So that's a remark that you have to, and that's the observation that you have. Okay. Now we come to the theme of today's lecture, namely Fatou's lemma. So we will make the statement of if you recall the monotone convergence theorem, Now you see, the limiting process and the integration process commute. Okay, the limiting process and the integration commutes provided you put an additional condition or a sufficient condition for this to happen is that GKs are all monotonically increasing. So only under that circumstance that we have proved this. Now you ask the question, suppose you drop this condition. Suppose you drop this condition. What can you expect? This is the question. Now we have seen an example where if you drop this condition, you cannot expect equality in all cases. There are situations where the equality is replaced by a strict inequality. Now which way the inequality goes? Now this is what is discussed in Fatou's lemma. So we'll make the statement. If Fn we have X is the measure space that we are working on, is measurable. Is measurable. Is measurable for each we have dropped that monotonicity, then what we have is this integral over x limit infimum of Fn. That's a statement. That means the limit infimum and the integral, they may not commute. Means the limit infimum. Or some other additional assumptions. The commutation of the limit and integral may not commute. This Fatou's lemma is essentially a caution that you cannot take it for granted that irrespective of conditions on the sequence Fn, these two operations will. On the other hand, suppose Fn is monotonically increasing, then what happens? This becomes simply the limit. This also becomes a monotonically increasing. It simply becomes, and in that case they are equal. This is what the theorem says. Okay. Now we give an example. We call the example the usual mu measure. Now we define Fn to be equal to chi of so what happens now? This is Fn is not there. Why? Because it is each Fn is 1 on the interval n to n plus 1, elsewhere 0. So if you take the sequence, now you see that at some stage, at some point, the function, that means if you take a Fn, it is specifically between n and n plus 1, it is 1. Or for all other n, this function is 0. Okay. So you get a sequences, if you take the value of the function at any point, it is going to be 0 for all values of n except for 1. This is what happens. So it's not a monotone sequence. Somewhere it breaks that condition. Okay. And we have seen that the integral and we have seen that the integral whereas limit this is equal to 0. So this actually converges to a identically 0. function pointwise. So Fn converges pointwise to the zero function. Which implies zero. So that is what this theorem says. Here in this case, limit inf and the lim are the same. So you see that we get 0. Wherever the limit exists, lim inf is the same as lim. Strictly less than So this is the example. This is one of the examples. You can construct now examples where these things are satisfied. Okay, so that's just the same example that we have earlier. Now we will just give the proof of this. Take put GK and for x belonging to then GK is less than or equal to. So that integral over measurability etc. is very well taken care of. Okay. Now you see that this each GK is measured. And that comes from the limits of measurable functions is measurable. Okay. Therefore, GKX by the monotone convergence theorem. We have limit f and d. But then this is different, okay? So we have computed this, limit k tends to infinity. But the other one is, of course, you cannot say anything. So this is less than or equal to. Therefore, the result, that's the result. So that completes the proof. Now we can once again come back to our one of the statements that I made earlier, namely, if you take non-negative measurable functions on x, you can construct new measures on x. Okay, so make that statement. So the next theorem corresponds. New measures can construct. So the remaining theorem, so the next theorem actually tells this. So this says the following. The extended real valued measurable function is measurable. And defined as is a measurable subset of x. That is what you have is x So naturally, you ask this question. Suppose you have the same measurable substance and I measure, find on this. Can you always connect with the function? This question is now. In that case, you can, interchangeably use this function and we'll address this problem for now. Then so phi, by choosing an appropriate phi, you can devise a new measure. So naturally, one of the questions at this stage is this. Suppose all these conditions are given and two measures are given, mu and phi. Can you always relate mu and phi through an integral of this kind? Oh, sorry. It's a measure space. Further, x with the range in integral over x g d phi. Gf. Okay. Now you can see this. If you recall the example that is read. Square. Now what is df? X. This is the original measure. The right measure that. Okay. Now further what happens? You take this one. If you take integral over x g d of square. This is equal to g integral of x over. Now d phi can be written as This df you are writing. This is df. Okay. So that you are writing as 2x. So this is the example. So when you rig or change the concept of length of intervals, you can see this working. Okay, let us. So all that we need to prove is this: that phi is not infinity on every e. Secondly, phi is countably additive. So what we have to prove is this. Now we first observe that it is countably additive. Disjoint they are all measurable sets, but they form a disjoint family. Let E be then what you have is this chi E of F is equal to sigma 1 to infinity which is equal to, but phi Ej is essentially integral over x chi dB. Therefore, by a previous theorem, we have proved that phi E equal to sigma 1 to infinity Ej. Now, is phi is a so that completes the proof. So now we may just make a remark which we normally do, and is reflected here also. Use this. We write remark equal to, as you have seen, that d of dx. Okay. So this is your f. This is your phi. Okay. So phi is this. So here phi is okay. So that's the usual change of variable that we talk about. Okay. So we conclude this talk here, and we take it up. Take up these topics further in the next lecture, sometime early next week. Okay. Thank you very much.